Hey, testing stage. Welcome to my talk, Who Will Guard the Guards Themselves? An Introduction to Mutation Testing. My name is Bas Dijkstra, and I'm an independent test automation trainer and consultant from the Netherlands. So, before I start talking about mutation testing, what it is, what it does, and what the benefits are, let me give you a little bit of background about the problem that mutation testing can help solve. We're testing a lot these days. We're testing in local development environments, we're testing in production, and we're testing anywhere in between. We're testing all of the time. We're constantly working to get information about the quality of the software that we're building, or about how our software is performing in production, for example. Because we need fast feedback, we need to be agile, we want to be able to react quickly to information about the quality, about possible defects, and so on. And a lot, because we need all of that quality information a lot faster these days, as fast as possible. We rely a lot on tools to help us get that information in a more efficient way. So in other words, we rely a lot on automation. Which means that development teams and organizations these days spend a lot of time writing automated tests, increasing their automation coverage. They're spending a lot of time and money and effort on automation, all in an attempt with the goal to get information about the quality of their system, about the quality of the software that they're building in a more efficient manner. And that's all well and good, of course. Automation is brilliant. Automation is fantastic. I've been working in automation for 16 years and I love it. So we spend a lot of time working on automation, writing automation. There's a problem, though, or a problem that I think we are too often missing something. We don't talk a lot about the quality of the automation that we write. We don't talk a lot about testing our tests. The more we rely on automation to inform us about the quality of the software that we're building, the more we rely on those automated tests as a safety net between a developer building a feature or making a change on their local development machine, and that same changed code being promoted, maybe even all the way to production. We rely more and more on our automated tests to help us get insights into the quality and into any unintended side effects of the changes that were being made. But we don't spend a lot of time and effort thinking about and getting more information about the reliability and the extent in which we can trust our tests. And I think that's a problem because tests can deceive us too. Tests can give unreliable and false information as well. And there's two main ways in which tests can deceive us. So the first one that I want to briefly talk about is the concept of what's called a false positive. A false positive is a test that fails when there's nothing wrong with the application. So in other words, the test fails because the test itself is built or executed in an unreliable way. The information that the test produces, so the error that it signals, the exception that it throws maybe, is due to the test itself not being reliable and not because the application contains a defect or an unintended change. These false positives, sometimes they happen continuously, which means every time you run a single test, it fails, even though there's nothing wrong with your application. So my reaction to those kinds of tests is very, very short, very quick. Or not to the test, maybe to the person who wrote that test, is why didn't you fix that? And if you didn't fix it, why didn't you just disable or even delete it? Because a test that continuously fails isn't going to give you a whole lot of useful information, really, other than, well, the test still fails. So these are, in my opinion, in my view, pretty quick to deal with. Another category of false positives are the tests that fail every now and then, which is what people typically call flaky tests. So maybe you run a test and then it fails, and you run it again and it passes, and then you run it again and it fails again. So there's you're not 100% sure before the test is run what the outcome, what the result of the test is going to be. And that's a little bit more difficult than the false positives that fail continuously. But there are a couple of main root causes, I think, for these false positives, and especially for these flaky tests. They're often they happen due to problems with test data, for example. So maybe some data that you expect to be present in a database or in a dependent system isn't there, or has been deleted, has been disabled, whatever. So test data is a very common source of these false positives, and especially of these false positives that occur every now and then, these flaky tests. Test environments can also are also a major cause of these false positives. Maybe there's a system that behaves in a way that you didn't really expect, or maybe a dependent component that you rely on is unavailable and you weren't informed that it wasn't available. This can also have negative effects on your test results. So this could also be a major cause of false positives. And the third one is problems with timing or synchronization. So, for example, some kind of third-party system responds, but it takes a little bit longer to respond than you expected in your test. Or another an example that you're probably very familiar with is if you're working with UI-based automation. So you expect a button to be present on a page, and it is there, but just it takes a little bit longer to render than you expected. So it will be there. There's nothing wrong with the application. It's just that you didn't wait long enough for the system or a page or a certain response to be present or to be in a certain state. So timing and synchronization are the third big cause of these false positives, and together with problems with test data and problems with test environments. There's another category of unreliable tests that can deceive you, that I don't think we talk about often enough. So we talk relatively often about false positives because everybody sees them. They make themselves known, and they mark your test suite or your build as failed. False negatives are tests that pass, so they give a nice green check mark. They don't complain, they don't whine, they don't scream, I failed. But they let an unintended change slip by. So they don't detect the change in your code that they were supposed to detect. And these are at least potentially much more problematic than false positives. Again, false positives are annoying. They generate a lot of noise. They scream, I failed a lot. But false negatives are the silent killers. They pretend, or they don't let you know that something's wrong because they pass, and passing tests are good, right? But false negatives are a lot harder to detect generally, simply because, well, they don't make any sound, they don't make any noise. So let's look at a quick example. So I've got a very simple representation of a bank account here, and the bank account has a type and a balance. The class has a constructor, and there's a method that calculates interest, which is, and it's passed an interest rate as the argument. And it only calculates interest. It only adds interest to the balance of an account if the account type is equal to savings. And we've got a test that creates a new account of type savings, deposits 10, adds 5% interest, and then checks that the resulting balance is 1050. So this is not, it's a pretty trivial example. It's not the best example, but it's just to make a point here, really. So this is what tests we typically look like. We have some code, and then we have tests that invoke the code. And in this case, the test will pass because it's a savings account type, and then add interest is called, and then it actually increases the balance. So the actual resulting balance is indeed 1050. So we have a passing test, and more importantly, at least for a lot of teams, we have 100% code coverage, meaning that all the statements in the code in the account class are executed when we run this test. And code coverage is, it's an interesting metric. And when I say interesting, I mean, yeah, it's I wouldn't rely just on code coverage. Is if I was interested in talking about having a conversation about the quality of my tests. And I'll show you why in a moment. But I see a lot of teams boasting, well, we have X% and X often is 95 or up percent code coverage. But let's now imagine your developer, or if you're a developer here in the audience, I'm talking about other developers. I'm not talking about you. I'm talking about other developers. It's not you. But they come in after a particularly exhausting weekend on a Monday morning, and they are tasked with refactoring, rewriting, adding some features to the code, maybe. And they think, well, this code isn't really written all that efficiently. I'm going to refactor some stuff. I'm going to improve some stuff. And in all the work that they do in adding to the code, refactoring the code, rewriting the code, whatever it is that their task of the day is, they accidentally rewrite the logic to always evaluate the true, which means that instead of interest being added only to accounts of type savings, interest is now added to all bank accounts. Again, this is a very trivial example. If you would ask me to implement the bank, I wouldn't implement it like this, but it's just to make a point here. Stuff like this happens. So they accidentally rewrite their logic, their code, to always evaluate the true. But, well, that's not a problem because they've got their tests, right? So they run their unit tests again, in this case unit test or the other types of tests, whatever. They run their tests again. The test still passes, and there's still 100% code coverage. So they think, well, it's all good. Let's put it into production. Let's publish this. Let's create a release. Let's give this to our customers. And that's where the problem happens. In this case, not for the customers, because now everybody gets interest added to this, and nobody, probably nobody will complain about that. But this is a problem for the bank itself, because now they have to pay a lot more money to their customers, to their clients, because there's a lot more interest being added to the balances of all these accounts than they expected. So again, this is maybe a pretty trivial example, but hopefully it shows that test coverage in and of itself is first of all, it's a great way to find code that's not tested yet. So it's a great way to spot gaps in your test coverage, really. But as a quality target in and of itself, as a means to inform you about the quality of the testing that you do, it's pretty useless. So is there a better way to trust our tests, or to trust our tests again? Yes, and that's by testing your tests. That's what it comes down to, really. And there's a couple of different ways, a couple of different approaches to do that. First of all, I'm a big fan of pair programming. Working together, that can be two developers, it can be two testers, automation engineers, it can be a tester and an automation engineer, it can be a tester and a developer. I don't care, really. But pair programming, or even mob or ensemble programming, where you pair program with groups larger than 2, is a great way to have instant synchronous reviews of the code. So the amount of bugs that slip by, or holes or gaps or problems with your tests, or with the quality of your tests, or just with your coverage, they will go down significantly if you have more eyes on the problem. An alternative for pair programming is code reviews. I much prefer doing pair programming instead of code reviews. Why? Because code reviews are asynchronous. So they often happen after the fact, and the people who originally wrote the code, who should receive the feedback about the work that they did, they've probably moved on to other tasks, other stuff. It's very disruptive. So code reviews are nice, pair programming is better. I see pair programming just as an inline, synchronous, real-time code review. And tests, like all code, tests evolve too. So it's a good idea, probably, to periodically, and what periodically means will differ from one context to the next, but periodically go through all of your tests again and see, are those tests still relevant? Are they still valuable? Are they still trustworthy? Does the information that this test gives me, is that still relevant? Is that still reliable? Is that still useful for me? I would do that fairly often. And again, what often means, it will vary from one context, one team to the next, maybe. But at least I would recommend making this part of your testing and automation strategy, to periodically review your test suite. And I don't want to go all Marie Kondo on you, but please don't be afraid to throw tests out. If it doesn't bring you value or joy anymore, just throw it away. Don't fall for that sunk cost fallacy where you say, oh, I spent so much time writing this test, I don't want to throw it away. If it doesn't bring you value anymore, if you can't rely on it anymore, you're better off without it. So please throw out those tests that do not give you joy and do not give you value anymore. And one thing that I always keep in mind when I write tests myself, but that I also try to teach to the people who are in my workshops, in my training courses, is when you write a test, when you run, and when your code compiles the first time and your test passes the first time, that's the moment where you should start seriously doubting yourself. I want to be, when I write a test and when I make that test part of a test suite that will run on every commit, on every release, every night. I don't care. I want to make absolutely sure that the test can fail. I want to be as sure as possible that I didn't accidentally introduce a false negative here. A test that always passes and lets changes that it's supposed to detect slip by accidentally. So never trust a test you haven't seen fail. That's a lot of work, testing your tests when you write them and periodically. Lucky for us, there's tools that can help us do that. And this is where we start talking about mutation testing. Mutation testing is a technique supported by tools that can help you in an automated way to get more information, more insight into the quality of your test suite. The way it works is what mutation testing tools do is they insert small changes in your application code. They create mutants. And a mutant is an in-memory copy of your application code base with a small change in it. And when I say small change, you can think about a flipped binary operator, for example, or a removed call to a method that doesn't have a return type, because if it has a return type, it'll probably generate a compilation error, and that's useless. But it's these kinds of changes. It'll replace some type of variable with a constant value, for example. We'll see plenty of examples in the live demo that I'll start in a moment. Once it has created all these mutants, all these in-memory copies of your code with small changes, it runs the tests, your test suite, against all these mutants, against all these modifications. And if at least one test is failing for each mutant, that means the mutant is killed. That mutant is detected by at least one of your tests. And that's a good thing. It means that your tests pick up on any potentially unintended change. But if all the tests are passing, meaning that there's a mutant, there's a change that is not picked up by any of your tests, that's worth an investigation. It might mean you need more tests. It might mean you need better tests. It might mean you need you reach some dead code in your application, for example. There's loads of different mutation testing tools out there for pretty much every programming language. The tool that I'm going to demo for you in this session is PyTest. PyTest is a mutation testing library for Java. And what I like about PyTest is that it's one of the very few mutation testing tools that's actively supported by industry. Traditionally, a lot of mutation testing tools have emerged in academia. And because it's a very formal academic way of looking at the quality of your software. So there's a lot of research has been done and is still being done in the area of mutation testing and proving proving correctness of software. PyTest is one of the few mutation testing tools that started off, that emerged in academia, but has successfully been adopted and is actively supported by industry. It's an open source tool. It's very straightforward to configure, which is definitely not true for all mutation testing tools, but that's what makes PyTest such a great candidate for a demo like this. And if you want to know more about the tool, pytest.org gives you all the information that you're looking for, really. Configuring Pit or PyTest is pretty straightforward. It's available as a Maven plugin, so I can just add it as a dependency, as a plugin dependency to my project. And then in the configuration section, I can select mutators, and mutators are the set of changes that the mutation testing tool will make in your code. So for example, a mutator is change all greater than signs to greater than equal and smaller than to smaller than equal, for example. That's a mutator. And if that mutator is active, is enabled, every time your mutation testing tool runs on your code base or part of your code base, it will replace all occurrences of that sign with the other one. So it will replace all occurrences of a greater than operator with a greater than equals operator, for example. And which means that mutation test is a deterministic process. And so it'll generate the same changes each and every time. It's not like it's fuzzing something or randomizing. It's very deterministic. So it's reproducible, which is very good if we're talking about testing. And you can, and I'll talk a little bit more about that in some implementation recommendations, but you can configure the subset of your code that you want to run mutation testing on, for example. If you want to run PyTest against your code, you can do that because it's a Maven plugin with a Maven command. You'll see that plenty of times in the demo, but I want to show it to you on the slides as well, so you can try this out on your own system as well. All of the code, the entire code base and all the configuration that I'm going to be using in the demo is available on GitHub, so you can clone it from there and try it out for yourself. So what this command does is it generates the mutants, it runs the unit test to try and kill the mutants, and it reports on the results, really. But let's have a look. I can talk about this until I'm blue in the face, but it's much more interesting to see this live in action. So I've got a code base here with, again, an account class, a slightly more sophisticated class that represents a bank account, and I've got a set of tests. So that account allows me to create a new account, to retrieve the balance, to make a deposit, to withdraw money, very important if you have a bank account, and it has an add interest method. And I've got tests that cover this functionality. So first of all, let's run these tests. It's useless to start mutation testing with a failing set of tests. So it's always a very good idea to, before you start applying mutation testing, to make sure that your tests actually pass, because it's going to use the tests and the test results to determine whether or not mutants were successfully killed. But in this case, we have a passing set of tests. And now the next thing I can do is run PyTest, invoke PyTest on this code base. I've configured PyTest in here with the exact same configuration that you just saw in the slides. So I'm running this on the examples package with the default set of mutators. This is a relatively quick process. If your code base is large, it means PyTest will probably generate a lot of mutants, and the mutation testing process will take a lot longer, because all of your tests are run against all of the mutants that are generated. So that means you probably want to be careful and want to start small when you start introducing mutation testing, and don't try and run all of your tests against all of the mutants that are generated from all of your code right from the start, because that'll take a lot of time, and it probably will generate a lot of signals and a lot of noise, which then take you a very long time to go through and determine, is this actually useful? So let's have a look at the report that was generated. Open that in a browser. There we go. Zoom in on the details for the account class. As you can see, green means good, as always in testing. And red, or well, salmon, pink-ish, means there's something going on here. There's two different colors. So light pinkish means no coverage. So mutation testing tools measure code coverage as well, but they do more. We'll get to that in a moment. So you'll see in this code base, in the account code base, there's a number of signals. Let's look at some of them in a little bit more detail. So first, let's look at this one. So this is part of the add interest method. It tells me that there's no coverage for the case where the account type is checking, because if I've implemented my account class in a way that whenever I try to invoke the add interest method on an account of type checking, an add interest exception should be thrown. But apparently there's no test that does that. In this case, I think it's an important bit of logic, so there should be a test. So this is the first kind of valuable information that mutation testing tools can give me. Code coverage tools can give you the same information, but it's useful information nonetheless. So let's start improving our test suite by adding a new test that I'm just going to call it add interest exception for now. And I'm going to create a new account of type checking. And then I'm going to assert that an add interest exception is thrown whenever I call the add interest method on this account. And I can shorten this even further to a method reference. So I've now got a test that creates a new account of type checking and then asserts that whenever I try to add interest to an account of type checking, an add interest exception is thrown. So let's first run the test to see if the test itself passes, which it should. And it does. So I've now got a test where previously I had 7. And now let's run mutation testing again to see if we also improved our mutation coverage here. And open the report. And as we can see, this section of the code is now all green, meaning that it's covered in tests. And PyTest has deemed the tests that we wrote good enough to pass the mutants, because there one mutant was created. It removed the conditional, or in other words, it replaced this equality check with false. So that's another type of mutation that a mutation testing tool can generate. So it just replaces a boolean, an expression that evaluates to a boolean with the value false, and it checks if that's picked up by any of the tests. And in this case, that is true, because our newly written unit test will pick that up, because it will fail. Because if this is false, then the add interest exception will not be thrown, even though it expects it to be thrown. So we're good in this section. The other part where we don't have coverage is this part. So, but if we look at our code, actually our IDE is already telling us something interesting here. This code is never used. So it is what we call dead or unnecessary code. So maybe we can just improve our code simply by removing this, because, well, there's no point in having code in your code base that's never used, that's never invoked. So let's see if that has a negative effect on our tests. It shouldn't, because that code is just never invoked. No, all of our tests still pass. And if we run mutation coverage again, let's see if we can bring back the figures here. And if we open the new report, we can see that our mutation coverage for this class has improved from 67 to 71. And that's simply because that piece of code is no longer, that dead or unused piece of code is no longer there. The final, so I'm not going to be able to cover all of the mutations and make this improve this code to 100% test score, mutation test score. But there's one other change that I definitely want to highlight, because it's a change that, or an improvement that's typical, that no code coverage tool will make you aware of, but that a mutation testing tool can give you, can present to you. And that's related to this code clause. So the mutation testing tool PyTest generated 3 mutants for this one. 2 of them were killed, 2 of them were detected by my unit testing suite, but 1 of them survived. So it if either this or this conditional is removed, that will be detected by at least one of the tests. But it also changed the conditional boundary, and that one survived, so that one was not detected. And in this case, what it did is it changed this greater than operator to a greater than equals operator, and the tests did not detect that change. Now, as you know, defects often happen especially around boundaries of equivalence clauses, so around boundary values. That's why boundary value testing is so important, and we all learn about the value of boundary value analysis and boundary value testing when we train and when we become test engineers. But in this case, we have a boundary where a slight change in the boundary is not picked up, is not detected. So that tells us we probably don't do a lot of, if any, testing around the boundaries here. So we might want to, and we probably want to, improve that. And in this case, in this example, there's a pretty straightforward change that we can make. So it's a good thing to know that if we create a new account, if that account is equal, if the account type is equal to savings, the default balance is 10, so we get a present from the bank whenever we open a new savings account, and for a checking account it's 0. That's why in this test I can create a new savings account, withdraw 5, and then the remaining balance is 5, because the initial balance is 10. So we do a withdrawal here, but we don't have a test that does something similar to this, that invokes, that works with the boundary value here. So, and the fix here is rather is pretty straightforward. So instead of withdrawing 5, let's withdraw the entire balance of our savings account. So let's create a new savings account, immediately withdraw the entire balance of 10, and then check that the remaining balance is equal to 0, which is true because our test passes. And now let's see if that helps improve our mutation coverage, and it helps improve the effectiveness of our tests in detecting any unintended changes. So if we open the latest version of the report again, we can see that the mutation coverage has improved to 76. And if we look at this statement, and especially at the first mentioned mutant here, the changed conditional boundary, that's now also killed, meaning that we now have a test that will detect an unintended change around the boundary value, so with the operators or the logic implemented in this piece of our code, which means we now have, and this even didn't require me to write in. I could have also written an additional test or a parameterized test with more examples. I could have done that, but in this case I just chose to change the existing test to exercise the same logic, but do that right on that boundary value. Again, there's a couple more signals in here. I don't have the time to go into all of them, but this one is it's good. I'm not going to fix it, but so this one is about removing. So it removed the call to this method entirely. This is a void method, so it doesn't have a return type. So it's just adding the transaction that you do to a transaction list. And my mutation testing tool tells me that, well, I removed this method call and none of your tests picked up on that. Meaning that I don't do any testing to verify that transactions that are performed, so deposits and withdrawals that are performed, are added to the transaction list that's kept for each individual account. And that's true, because if you look at the account test, there's no test in there that does any verifications on the transaction list. So that's another area where I can improve my tests. But I'll leave that up to you. So again, all of the code is available that I'll show you is available on GitHub, so you can run that from your own machine as well. I'll give you the link in a moment. I'm going to leave this one for you to fix, as well as the other signals that are still in the report. So in conclusion, wrapping this up, this is, first of all, I hope I've been able to give you some more insight into how tests can deceive us, how test results can deceive us, and why it's important to spend a little bit more time and energy talking about investigating the quality of our tests, the reliability of our tests. And I've tried to give you an example, give you a very brief introduction into mutation testing as a tool that can help you get that information. And it's probably, it's good to remember that, again, mutation testing tools can do everything that code coverage tools can do, which we just saw, but they can do more than that. So there's a lot of potential problems with your test and your test suite that mutation testing tools can bring to light that mere code coverage just isn't going to tell you anything about. So if you want to get started with mutation testing, I think more people and teams should do this. I think it's a very valuable technique that can give lots of valuable feedback about the quality of your tests that you're doing, and not just the quantity. But I wouldn't use it on all of your code. Because again, if you have a large code base and you run mutation testing, a mutation testing run can take a very, very long time and generate a lot of information, a lot of signals that you then need to go through. So my advice is, with so many things in code, in software, and in life, is to start small, see what value it brings, and then learn from that. And then keep what you like, keep what you love, keep what's bringing value, and stop using what doesn't. In general, I think it works especially well for tests around algorithms, around business logic. So the examples that we've just seen with the bank account. The most important and the most interesting information that the mutation testing tools gave us, that the mutation testing tool gave us, is around how we test and how well we test our business logic. And that's where I think mutation testing really, really shines. Again, I just add all of the code that you've seen in this talk, in this demo, is available on GitHub. It will remain available on GitHub for probably for a long while. So by all means, check out that code, run it on your own machine, and just see if you can make sense of the information that mutation testing can give you about the quality of your tests. That wraps up my talk. Thank you so much for taking the time to listen to my talk, to learn a little bit more about how tests can deceive you, how mutation testing can help you get more information about, get more insight into the quality of your tests. If you want to get in touch with me, if you have additional questions that you're unable to ask right away during the event, by all means, reach out via email. I'm more than happy to talk to you about mutation testing or anything testing or automation. And also check out my website. There's a blog that I update regularly. You can subscribe to a weekly newsletter. And there's more information about the professional services that I provide. Again, thank you very much. Have a nice day. Enjoy the rest of the testing stage event, and I hope to see you again somewhere in the future. Thank you.